Capstone 5. Sea level rise and coastal systems. One of the IPCC's most recent reports on climate change provides insight into the impacts, social, economic, and environmental consequences of a 1.5 degrees Celsius of global warming and related GHG emissions compared to a 2.0 degrees Celsius above pre-industrial levels. The findings suggest that climate-related risks for both natural and human systems are sufficiently higher for global warming of 1.5 degrees Celsius than at present, but much lower than at 2.0 degrees Celsius. One of the major regions threatened by the impacts of global climate change is the coastlines. Coastal areas are hubs of human socioeconomic and cultural developments. They are also home to critical environmental and ecological resources. While climate change poses a myriad of risks to coastal environments, the foremost among these threats is sea level rise, caused by an expansion of water due to rising atmospheric temperatures and melting ice sheets. Besides threatening people, ecosystems, and build environmental directly, SLR also magnifies the impact of storms and storm-induced flooding. Hurricane Katrina impacts on New Orleans, Louisiana, in the United States in 2005 provides a glimpse of what can befall low-lying areas if coastal management systems fail or are non-existing. A list of coastal cities threatened by SLR is long. New York City in the United States, Amsterdam in the Netherlands, St. Petersburg in Russia, Victoria, Bangkok, Alappuzha, Alexandria, Sutso, and Mongo Gran Canaria are but to name a few. However, Miami, Florida in the United States, and Osaka, Japan, are in the front line. These two cities are vulnerable for several reasons. They are both densely populated and low-lying. These cities are also frequently battered by unseasonably strong storms and relentless rain. Apart from being flat and low-lying, Miami and Osaka SLR problem is a vexing geological one. In Miami, for instance, the solid ground underneath the city and much of the rest of the Floridian Peninsula is mostly porous limestone, meaning that salty seawater is seeping into and rising through the ground itself to exacerbate the flooding problem. Osaka, like Miami, is sinking because of the weight of infrastructure development as the increased building activities are causing the land to subside. Osaka is also losing foundational sediment to periodic typhoons, heavy rains, and flooding that would naturally protect the city. Together, Miami and Osaka also face heightened SLR threat due to coastal sedimentation starvation. This threat arises from sediment compaction caused by anthrogeogenetic engineering activities. In terms of environmental change, forecast indicates that SLR is likely to rise by 9 to 18 centimeters by 2030, 15 to 38 centimeters by 2050, and 30 to 100 centimeters by 2100. Emerging evidence regarding the stability of the Antarctic ice sheets implies that at high GHG emission scenarios, SLR exceeding 240 centimeters by 2100 is physically possible. The impacts of SLR are numerous and include wetland loss and change, accelerated intrusion, heightened coastal erosion, population displacement, saltwater intrusion, and higher water table resulting from impeding drainage. Possible solutions to these impacts include building a network of seawalls and other coastal defense systems such as dike and surge barriers, enacting and revamping building codes that foster the construction of flood-resistant buildings, and instituting sustainable land use policies.